Consider an array representation of n elements binary heap where the elements are stored from index 1 to the index n of the array. Okay. For the element stored at index I, where I is less than or equal to n, the index of the parent. So we have to find index of the parent. So if you have a heap like this, right? So let's assume this is x, this is y, and this is z. So in the array, right? So the first element will be x, the second element will be y, and third element will be z. And it is given that the index starts at 1. So here it is 1, this is 2, and this is 3. And we know that the parent of y is x as well as the parent of z is x, right? So if I give the index 2, I should be able to get the parent as 1, right? Similarly, if I give 3, I should be getting as 1, right? Because 2 and 3 both are having the parent x, right? So I can say that 2 by 2, that is equal to 1. Now 3 by 2, that's also should be 1, right? So basically we have to do the floor, right? Floor operation we have to apply, right? So then only we'll get 1. So the correct answer should be B. The following elements are inserted one by one in the given order into a max-heap. The resultant max-heap. So we have to find the resultant max-heap, and it is given that we have to insert the elements one by one to a heap, right? So we all know the insertion procedure. So the first element will be 32. If you see all the trees, all the heaps given here is having 32 as the root, right? Then we have 15, that will be in the left. Then we have 20, so we'll insert in the right. Then we have 30, so we have to insert in the left, right? So before inserting, we will check with the parent, and we will see that okay, here the value is 15, right? So we have to swap these two, right? So our new tree will be 32. Then we will have 30 here. Then we have 15. Then 20. Okay. Now, one thing you should understand that this value 30, right? This value 30. Now it is in the left side. Okay. So it can move to the right side only when once it has to move the value to the root, then it is possible that it may move to the right, right? But if you see, we have 32 here, right? That means our value 30 will never move right of this heap, right? So that means choice B is wrong because 30 is in the right side, and also choice D is also wrong because 30 is in the right side. See, I am not saying that 30 will not move to the right side. 30 will move to the right side only once it's moved to the root. But we have 32, that is the largest element. So we know that 30 can never move to the root, right? So once it moves to the root only, it can move to the right. Okay. So that means choice B is wrong, choice D is wrong. So the answer may be A or C. Now if you see the choices A and C, this portion is same. So I can insert 12 here, right? Now if you see the right side, okay, again you have 25 here. See 25 here, right? 25 is here. So before that 12 is gone, right? 12 is gone. So you will be inserting 25 in the left side. 25 will be inserting the left side, but you cannot do like that. So 25 will be here, then 20 will be here. See, now 20 is here in the left side. Okay, this 20 will not move to the right side because you have 25 here, right? So definitely the 16 should be here. So the answer should be A, right? If you see here, you have 16 in the left side and 20 in the right side. That is not possible. So this should be the answer. See, you don't need to really do like this. You can actually simply insert one by one to the heap. I am just showing you that sometimes we may be able to figure out which one of this is correct choice without really doing the insertion. A priority queue is implemented as a max heap. Initially, it has 5 elements. The level order traversal of the heap is given below. So this is the level order traversal. So we know that the heap will be 10, right? It it is very easy to draw heap once you have the level of traversal, right? This will be the heap. So we have to insert 1, right? So 1 we have to insert here, right? 1 we have to insert here. We can directly insert here because the root is having the higher value. Then we have to insert 7 in the right side, right? 7 should be in the right side. But as we know that 5 is here, right? We have to move 5 here. So this value will be 7 and this value will be 5. Okay. So it's clear that the last value should be 5, right? So in that way itself we can actually remove the choice A. Anyway, just do the level of traversal because it's easy. So the first value will be 10, then 8, then we will have 7, then 3, 2, 1, 5, right? So the choice D is the correct answer. Which one of the following in-place sorting algorithm needs minimum number of swaps? So here swaps means basically the record movements. So as we know that this is a direct theory question, so we know that the selection sort, right, is in the worst case it takes only order of n swaps. All other algorithms are going to take more swaps, but selection sort, one of the important property of selection sort is that it needs minimum number of swaps. So the answer is C. In a binary max heap containing n elements, the smallest element can be found in time, or we have to devise an algorithm to find the smallest element from a max heap. So what we know about max heap is that you have the maximum element in the root, right? Maximum element in the root, and let's assume you have some nodes, you have some keys, something like this. So what you should note that in a max heap, the minimum element will be in the leaf. The minimum element will be in the leaf, and we know that approximately we will have n by 2 elements in the leaf, right? So approximately you will have n by 2 elements. So you have to basically compare this n by 2 elements to find out the smallest element. So that will take at least n by 2 comparisons. So we can say n by 2, we can remove the by 2, right? So n by 2 is nothing but this is a constant, so we can remove. So we need to have order of n time to find the smallest element from a max heap. So the answer should be A. Consider the process of inserting an element into a max heap where the max heap is represented by an array. Suppose we perform a binary search on the path from the new leaf to the root to find the position for the newly inserted element. The number of comparisons performed. Okay, so what we should understand one thing. We have, if we have a heap like this, okay, and let's assume you are going to insert an element here. So one thing we should know that this is a complete binary tree. So the height of this tree is log, right? The height of this tree is log. Now we are going to insert an element here, right? And that element may be ending up here, or it may be ending up here, here, or here, right? So that may be in this path, right? One more thing you should understand that if you take all the elements in this path, okay, if it's a max heap, then that will be a sorted array, right? This will be a sorted array, right? If you assume only the elements here, then you can see that these elements will be a sorted array, right? Or you can assume it's a sorted array. Now that array will have log n elements, right? Log n elements. Now we are asked to find out the where that element actually is getting inserted. So we can use binary search. That is what it's mentioned in the question itself. We can use the binary search. So we know that if you have n elements, the binary search is going to take log n time, right? So if you have log n elements, the binary search is going to take log n time, right? So the answer should be B. We have a binary heap of n elements and we wish to insert n more elements. It's given that we don't need to really insert one after the another into this heap. The total time required for this. Okay, so we know that if you have n elements, right? If you have n elements and if you want to insert one element, or if you want to insert element one after another, so every element is going to take log n time, and if you want to insert n more elements to this, it is going to take n log n time, right? But it's given that it is not necessary that you have to insert one after the another. So let's assume all these 2n elements are in this array. So you have 2n elements, okay, and it is okay that we have a heap here, okay, that is having n elements, and remaining n elements are here, okay, remaining n elements are here. Now you just assume that you have to construct a heap from 2n elements, ignoring the fact that you have a heap of n elements here. So now the question is simply, you have 2n elements, how to construct a heap, right? So we know that if you have n elements, we can construct the heap in order of n time. So if you have 2n elements, you can construct a heap in order of 2n, right? So this 2 is a constant. So that means we can construct a heap in order of n time if you have 2n elements. So the answer should be B. Which one of the following array represents a binary max-heap? So this is the level order traversal or the array representation, right? So we can directly see that whether A is a heap or not just by drawing 25. Then you have 12, here you have 16, here you have 13, here you have 10, right? Here you have 8, and here you have 40, right? This is not a heap. This is not a heap because here the heap property is getting violated, right? Because you have 13 as a child of 12, so that actually violates the heap max heap property, right? Or without drawing also you can see here, because we know that 25, right? So 25 will have these two as child, and we know that both are less than 25, and 12 will have 13 and 10 as child, and we know that 13 is greater than 12, so choice A should be wrong. Now if you see the choice B, 25 will have 14 and 13 as child, so that is okay. Now if you take 14, right, it is clear that you will have 16 and 10 as child, but the heap property is violated, right? So choice B is wrong. Now if you take choice C, you have 25 here, right? So 25, this will be the child, that is okay. Now for 14, you will have 13 and 10, that is fine. And for 16, you will have 8 and 12. So this is a valid heap. Now if you see the choice D, for 25, you have 14 and 12. And for 14, you have 13 and 10, that's fine. And for 12, you will have 8 and 16, that is here. If you see, this 16 cannot be the child of 12, right? That will violate the heap property. So choice D is wrong. So the correct option is C. You can even draw the heap and then you can verify it. What is the content of the array after 2 delete operations on the correct answer to the previous question? So I just drawn the solution from the previous question here. So this was the correct heap. Now we want to delete. We want to perform 2 delete operations, right? So that means we have to delete 25. So once we delete 25, what happens? Basically, we will copy this 12 to this root. Then we'll call heapify, right? So if you compare this 2, 16 should be here. And left side, there will not be any change. 14, you will have 13, 10, right? Then here you can have 12 and 8. So this will be the result after we call heapify. Now we have to do one more deletion. So basically you delete the 16. That means you have to copy 8 this location and call heapify, right? So that means 14 will come here, 14 will come here. So right side will be 12, right? Then you will have 13 here, then 8 and 10, right? So this will be the result after we call heapify, right? So the correct level order traversal should be 14, 13, 12, 8 and 10. So the correct option should be D. This is a simple question. Which of the following is a max-heap, right? So the choice A, this is not a complete binary tree. So this is not a heap. And if you see this choice C, we have 8 as a child of 5, right? This is violating the heap property here. So this is not a valid heap. Now if you see the choice D, 10 is a child of 8. So here again it violates the heap property. So choice D is wrong. And the correct option is B. Now if you see all the internal nodes here are having less value than 10. Similarly, all the nodes in the right is also having a value less than 10. Now if you take any node, if you take 8, that's having 2 children, both are having value less than 8, and here you have 6 and both children are having value less than 6, right? So this is a valid max-heap. Consider the following array of elements. So we have a set of elements in an array. The minimum number of interchanges needed to convert this into a max-heap. So let me draw the array as a heap. So we have 89, 19, 50, 17, 12, 15, 2, 5, 7, 11, 6, 9 and 100, right? So if you see this heap, all the elements satisfies the heap property except this 100, right? So basically we have to move this 100 to here, 15 to here, that is one swap. Then we had to move that 100 to here and 50 to here, that is 2 swaps. Then we had to move the 100 to here and 89 to here, right? So the new tree will be 100. Left side there is no change. Right side you will have 89. Then you will have 50. Right side you will not have any change, right? So then 50. Then you will have 9 and 50, right? So this is a heap. So the minimum number of interchanges what we are doing is 3. So the option D is the correct answer. A complete binary min heap is made by including each integer 1 to 1023 exactly once. So we have 1023 elements, right? The depth of a node in the heap is the length of the path from the root of the heap to that node. So the root is at depth 0. The question is the maximum depth at which the integer 9 can appear. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 up to 1, 0, 2, 3, right? Now let's try to construct. So what we know is that the root will have the element 1, right? Because we are constructing a min heap. So the minimum element should be in the root. So I can say that in this set of elements, the minimum element will be always at depth 0, right? So what I know is that the minimal element will be at depth 0. Okay. Now what about the second smallest element. So second smallest element may be here or it may be here, right? Because we have a lot of elements. So if we are not keeping the second element at this level, we cannot move further from that particular node, right? So what I know is now the second smallest element will be always at depth 1, right? So second smallest will be at depth 1. Now what about the third smallest element? Okay, so I can place, for example, 1, 2, 3 like this. So the third smallest element can be at depth 1, okay, or instead of 3 here, right, I can keep 4 here and then I can place 3 here, right? So this third smallest element can be at depth 1 or 2, right? So the maximum depth at which this third smallest element you can place is at depth 2. Now let's see the fourth smallest element. So the fourth smallest element is basically this one, right? So as we know in this figure, we are actually placing 4 in the depth 1. So I can place fourth smallest element at depth 1, right? At depth 1, and I can also draw like this 1. I can have 2 here. I can have 3 here. Then I can have 4 here, right? So the fourth smallest element can be up at depth 2. Now I can actually do like this 1. Let me place 2 here and 3 here and 4 here. Okay, then I can place some numbers here. For example, I can have 5 here, right? Then here also I can have 6. Here I can have 7. Here I can have 8. Right? Here I can have 9. So what I'm saying is the fourth smallest element can be at depth 3. So if you see the fourth smallest element, if you see the maximum distance I can keep it from the root is actually 3. Similarly, the third smallest element, I can make it at depth 2, and second smallest element will be, this is always at depth 1, but third and fourth, you can keep it at 1. Third, you can keep it at 1 and 2. Fourth, you can keep it at 1, 2, or 3, but the maximum is 3. So if you think like that, the ninth smallest element can go up to maximum depth of 8, right? Maximum depth of 8. So the answer should be here 8. One more thing you should understand that. So let's assume you need to have enough elements to place this in the 8th position. Okay. What I want to say is, if you try to keep it in the depth 8, so if this is the heap you are expecting, for example, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, if this is the way you are actually trying to create, then only you can actually have the depth 8, right? So here the depth is 0. Here 1, 2, 3, 4, 5, 6, 7, 8. If this is the way you are going to create, then one thing you should be clear that you need to have, see, up to this level completely filled, right? Then only it will be a complete binary tree, right? So up to this level should be completely filled. So that means you need to have minimum 2 raised to 8 minus 1, this many elements, okay, right? Then only you can place this 9 here. But we have around 1023 elements. So there is no issues of placing like this. So the answer should be 8. In a heap with n elements, with the smallest element at the root, that's mean heap, right? The 7th smallest element can be found in type. Okay, so you have a heap and you have to find the 7th smallest element, right? So you have a heap, something like this. Okay, so you know that the first smallest element will be in the root, so you have to basically do that in constant time, and the second smallest element will be in depth 1. So here basically you have to compare these two elements, right? So whatever may be the size of the heap, you have to basically compare these two elements. So again it is a constant time. So the third smallest element will be maximum will be at depth 2, right? So basically you have to compare these 6 elements to find the third smallest element. That's also a constant time, right? Because whatever may be the size of the heap, you have to always compare the 6th element to find out the third smallest element. So similarly, if you think the 4th smallest element will be maximum up to here, right? So 5th, 6th, 7th, or 8th, or 9th, basically what I want to say is, if you see the 7th smallest element will be at maximum distance 6, right? So basically you have to see 2 raised to 7 minus 1, that is equal to 127, right? So maximum you have to compare, or you have to search in this 127 elements to find the 7th smallest element, right? So you don't need to worry about the size of the heap. So whatever may be the size of the heap, for example, if the size of heap n is equal to 50,000, still you are actually finding the 7th smallest element in this 127 elements, right? So the size of the heap is not actually depending on your idea to find the 7th smallest element, right? So I can say that the time complexity will be constant because it's independent of the size of the heap. So the answer should be D. The number of possible mini heaps containing each value from 1 to 7 exactly once, right? So we know the structure of the heap should be like this. Now we can use the combinatorics idea to find out the minimum number of heaps, or we already know how to do this using this tree, right? So what our idea is, we have to, for each node, we have to count the number of nodes in the left subtree plus the number of nodes in the right subtree plus 1, right? So here we will have 7, here we will have 3, here also we will have 3, and here we will have 1, 1, 1, and 1, right? So the answer should be, we have 7 elements, so it should be 7 factorial divided by 7 into 3 into 3 into, then we will have 4 ones, right? So 7 factorial is nothing but 1 into 2 into 3 into 4 into 5 into 6 into 7 divided by 7 into 3 into 3, right? So this 7 and this 7 we can cancel, this 3 and this 3 we can cancel, this 3 and this 6 we'll get 2 here, right? So we have 2 into 2, that is 4, 4 into 5, that is 20, and 20 into 4, that is 80, right? So the answer should be 80. A data structure is required for storing a set of integers such that each of the following operations can be done in order of log time, where n is the number of elements in the set. So we have 2 operations to support. One is deletion of the smallest element, and second operation, insertion of an element if it is not already present in the set. Now, which of the following data structure can be used for this purpose? So if you see these choices, in all the choices we are comparing the heap with a balanced binary search tree, right? So let's see what are the operations and properties of heap that it supports. So one thing, the deletion operation is supported. So if you have a min heap, you can delete the minimal element in order of log n time. Second, insertion is also supported, and it takes order of log n time, because we know that heaps are actually complete binary tree, and the insertion and deletion algorithm actually is going to take the worst case, it's going to take the height of the tree, and we know that the height will be log n because it's a complete binary tree, right? Then what about search? If you see, the basic data structure of heap does not support the search operation. So basically, if you want to search in a heap, you have to consider it as an array and start from the beginning to end to search for an element. So it is going to take order of n time. Another important property of heap, usually heap can have same values multiple times, right? Same value multiple times. Okay. Now let's see the balanced binary search tree. So this may be a AVL tree or a black tree or B tree or B plus tree, or are balanced binary search tree. And the important thing you should note is that all the balanced binary search trees are having height order of log n. Okay, that is why it is called balanced. Now let's assume if you want to delete an element, that can be done in order of log n time in binary search tree, in balanced binary search tree, and similarly you can do the insertion in order of log n time, and also it's a balanced binary search tree and main intention to search, so search also can be done in order of log n time. Okay, now let's see the operation. So the deletion of the smallest element, so that can be done in heap in order of log n time. Now if you use a balanced binary search tree, first you have to find the smallest element. So you have to search for the smallest element. That will again take search. Smallest element is also supported by balanced binary search tree, so that also will take order of log n. Then you can delete, so that also is going to take order of log n. So log n plus log n is log n. So that means both data structure can delete the smallest element in order of log n. Now insertion of an element if it is not already present in the set. Now if you see the heap insertion, we are just going to insert, we are not going to check whether that element is already present or not. So this operation, if you want to use heap, you have to implement like first search for it, right? First search for that element. If that element is not exist, then we have to call insertion. So you have to have a search here. So that is going to take order of n. So this operation you cannot do in log n time using heap. But if you see the balanced binary search tree, you can search in log n, and if you are able to find it, you can leave, or if you are not able to find it, you can insert. Again, that is going to take order of log n. So heap cannot be used for this operation. I mean, if you use heap, you have to have order of n time. You cannot do this in order of log n time. So the correct answer should be B. A balanced binary search tree can be used, but not a heap. So we have 4 statements here, and we have to find out which of the above statements are true. Now the first statement says the smallest element in a max heap is always at leaf node. That is true, right? You need to have the smallest element in the leaf node of a max heap. So this statement is true. So that means choice D is wrong. Now the second statement says the second largest element in a max heap is always a child of root node, right? So it says, we also know that the second largest element can go to maximum depth 1. That means it should be the child of the root node. So second statement is also true. So that means choice C is false. Now if you see, you have A and B, and the difference here is third and fourth. So we had to basically see one of these should be false, right? So let's see the fourth choice. What it says: a binary search. This is very important property. Okay, a binary search tree can be constructed from a max heap in order of n time. Okay, so let's assume this statement is true. Let's assume this statement is true. We'll prove that this is false, but let's assume this statement is true. Now, certain things you should understand. Okay, one thing that in a sorting, in a comparison based sorting, in a comparison based sorting, the lower bound of sorting is order of omega of n log n, right? That means you cannot sort an array using comparison sort based sorting with less than n log n time complexity in the worst case. So that is the meaning. So you need to, if you want to sort using comparison based sorting, it will take n log n time. So that is already we know there is a proof for this. Okay. Now we assumed that this process is true, right? Now we know that this fourth choice is a binary search tree can be constructed from a max heap in order of n time, right? So let's assume you have a heap. So heap, and we know that we can construct the heap in order of n time, right? We know that we can construct the heap in order of n time. Then the choice says that in order of n time, you can convert this heap to binary search tree. So binary search tree. Okay, now my question is how much time you need to create a binary search tree from set of n elements. What you will do, you will first create the heap, then convert that into binary search tree, right? So order of n plus order of n will take only order of n time, right? Now also we know that the in-order traversal of a binary search tree actually gives us the sorted order, right? Now how much time the in-order traversal is going to take, that we know it is order of n. Now if I want to sort n elements, what I will do, I will first construct a heap, then convert that into binary search tree, then do the in-order traversal. So I can do the sorting in order of n time, right? So construction of heap takes order of n, plus the conversion takes order of n, then the in-order traversal take order of n. So if I add all these things, it will be again order of n. So that means I can sort an array in order of n time. That is not possible, right? So in a comparison based sorting, you need to have minimum n log n. So if this conversion is possible, that means you can sort in order of n time. So the fourth option is wrong. So choice B is wrong. So the correct option should be A. Now let's see the third choice. It says a max heap can be constructed from a binary search tree in order of n time. That is true, because you have a binary search tree, you can do maybe in order traversal that will take order of n time, then store that elements in an array, right? So that array A, we need to convert into a heap so that we can do it in order of n time, right? So you have to just copy that into an array and just convert that to a heap that will take order of n time. So this statement is true. So the question says we have a heap data structure and we want to implement delete I. So I is the index of the array. So basically we want to delete an element if the index of that element is given in a heap. So we know that usually heap supports only deletion from the root, right? So this question is asking us to basically design an algorithm to delete any element from a heap. Okay, and it's given that the depth is d. Okay, the depth of this heap is d. So I can even say if I have n elements, then d should be actually log n, right? Log n. So anyway, here it is given directly the depth as d. Now what is the time needed to refix the heap efficiently after the removal of that element. Okay, so let's see a heap, something like this. Okay, and let's assume you're going to delete the element at index 2. Okay, so um, and let's assume it's a max heap. So this will be the maximum element. This will be the maximum element, right? And you are going to delete this element. Okay, so uh, if I delete this element, basically you are actually removing one element from the heap. So the heap structure is going to change, right? So you will not have this node in the heap after this, right? So what I can do is I can actually just copy this element to here, because we are actually deleting this. Now if I copy this element here, one thing you should understand, that only the heap property will not be maintained here, right? All other nodes are having the heap property because it's initially a heap, and I'm just changing one value here. I'm just copying this element to here. So here I will be losing the heap property, right? So I have to basically call heapify from here. Heapify from here. Okay, so I know that the time complexity of heapify will be the height of the tree, right? In the worst case, you may be deleting an element from the root. In that case, we have to copy that element to the root, right? And then call heapify, right? So the worst case, it will take the height of the tree, and it is already given here that the height of the tree is d, right? So it will take order of d time to delete a random element from a heap. So the answer should be order of t, but it's not constant, right? It is not constant, it is order of t, right? So the answer is B. So the question is number of elements that can be sorted in theta of log n time using heap sort. Okay? So we know that if you have n elements, then you can sort using heap sort. It will take theta of n log n time, right? So if you have k elements, then it will take theta of k log k, right? So it's given that you are taking only log n time. Okay, so it's given that heap sort is taking log n time. So the question is, then how many elements you can sort in log n time, right? That is the question. So let's take the choice D first. That looks easy for me. So it says that if you can sort log n time, you can sort log n elements. Okay, log n elements using log n time, right? So if your k is equal to that is what we had to find, right? So let's assume the k is equal to theta of log n. So k is equal to theta of log n. Then the time complexity of heap sort will be equal to theta of k is log n, right? So log n into log n, right? So this is not equal to log n. So k is equal to theta of log n. This is wrong. Let me take k is equal to root log n. Then the time complexity needed for the heap sort will be equal to theta of k is equal to root log n, right? So root log n into log into root log n. So this will be the time complexity. So that is also not equal to theta of log n. Now let's me take theta of 1. So if k is equal to theta of 1, that's order of 1, then the time complexity should be of the heap sort should be equal to k is now theta of 1. So 1 into log, or 1 is some constant, right? So some constant into log some constant. So some constant into log some constant will be a constant. So that is actually theta of 1, right? So this is also not equal to log n. So the answer should be C. Anyway, let's see. So let's assume k is equal to log n by log n. Now the time complexity of heap sort will be equal to eta of, right, k is now log n by log n, right? So log n by log n into log n by log n, right? Now this is in log a by b format, right? So I can write it as, so let me delete some portion. So let me write this equation again here. So we have log n by log n divided by log n into log, see, log a by b is equal to log a minus log b. So we have log n minus log n, right? Log n. Okay. Now this is the theta notation, and we want it to be equal to log n, right? So if you see here, log n minus log n. So this is actually a lower term compared to the log n, right? So since we are interested in the theta notation, we can actually remove the lower terms, right? So log n minus log n. So I can remove the log n. So and this log n and this log n can be, we can cancel it out, right? So I'm getting theta of log n. Okay. So the correct answer should be log n by log n. A priority queue, capital Q, is used to implement a stack. So basically we want to implement a stack using priority queue. Okay. So we have stack operation push C. So that push C will be converted as insert into the priority queue with the value C and a key, right? Because a heap works with a key, right? So where k is a appropriate integer key chosen by the implementation. Okay, and pop is implemented as the delete min queue. So that means the question is actually how to implement a stack using a min heap, right? So it is something like a min heap because we have delete min. So it's a min heap, and using this min heap, you have to implement a stack, and we have 4 choices. Now the key should be non-increasing order. So what's non-increasing order? Non-increasing order means it's not actually decreasing, right? For example, if you have key from 1 to 10, the non-increasing order can be something like 10, 10, 10, 9, 9, 8, 7. This is non-increasing. Okay, it is not, these excessive numbers are not increasing, so it can be equal. Okay, similarly, non-decreasing means, for example, you have the keys from 1 to 10, you can say that it's non-decreasing. That means you can have 1, 1, 1, 2, 2, 2, then 3, then 4, then 5, 5. So this is an example of non-decreasing order. Okay, I think we all know what is strictly increasing and strictly decreasing. Okay, now let's see a stack, and we have to insert P, Q, R to the stack. So if you insert one by one, the first, let's assume we are inserting P, then P will be here, then Q, then R, right? So if I pop, the first element coming out of the stack will be R, right? So that is the property of stack. Now we want to implement, let's assume we are going to use non-increasing order. Okay, now instead of push, you will have, right, you will be inserting the Q, there what value you are inserting is P, and let's assume you are following non-increasing order. So let's assume you are keeping the key as 10. Okay, now the root will be, right, something like P comma 10. Then let's assume you are inserting R again, and you can give the value key again 10 because it is non-increasing order. This condition is satisfied. So you will have Q, sorry. So you will have here R and the key is again 10. So it's a min heap. So the child should have value less than or equal to the root. So that is satisfied. Again, I can give the next value. Sorry, here I have to give Q, right? Sorry, here I have to give Q. And the next value is, let's assume R. That also I am giving 10. So that will be in the right side, right? So if I delete min, the element P is coming out, but we are expecting that the value should be R, right? So choice A is wrong. So the same way you can try for B. B also you can prove that it is wrong. Now let's see the choice C. It says strictly increasing order. So let me assume we are giving the keys like 1, 2, 3, that is strictly increasing order, right? Then we have a min priority queue. So the first element we are inserting is P. So we'll have P and 1. 1 is the key. Then the next element is Q. So we are inserting P, comma 2, right? So the it is a min priority queue, and the condition is that the children should have value greater or equal to parent. So that is satisfied. Here it will be Q. Sorry, here it will be Q, right? And the next is R, comma 3. Here also this condition is satisfied. So if I am taking back, I'll be if I am deleting, I'll be getting P. So this is also wrong. So the correct option should be the keys should be in decreasing order. For example, the order can be 10, 9, 8, something like this. Okay. So for example, let's assume you have 10, 9, 8. This is the order. So you'll first insert P, comma 10. Then you will try to insert Q, comma 9. Okay. Now this is not satisfying the min heap property. So I have to move this node to here. So I will be having Q, comma 9. Then I will have P, comma 10. Then the next I will be inserting with key 8, right? So R, comma 8. Now again you see the heap property is violated. So I have to move R, comma 8 to the top, and left we will have P, comma 10, and right we will have Q, comma 9, right? Now if I delete, the first element coming out of this priority queue will be R, right? So that is the expected behavior. So the answer should be D. Consider the array representation of a binary min heap containing 1, 0, 2, 3 elements. The minimum number of comparisons required to find the maximum in the heap is dash. So note that we had to have an exact value here. We are not expecting the approximate value. We have to find the exact number of comparisons, minimum number of comparisons, and that should be the exact number. Okay. So it's given that we have 1, 0, 2, 3 elements. So that means it is a full binary tree, right? So you have 2 raised to 0 here, 2 raised to 1 here, then you have 2 raised to 2 elements here, you will have 2 raised to 3 elements here, right? Up to and the last level, you will have 2 raised to 9 elements, right? Then only we will have 1, 0, 2, 3 elements. So the last level, that is we have leaves, we have 2 raised to 9 leaves, okay? 2 raised to 9 leaves. So 2 raised to 9 is nothing but 512. So we have 512 leaf nodes in this heap, okay? Now we also know that it is a min heap, and the maximum element will be in the leaf, right? If you have a min heap, then the maximum element will be in the leaf. So we know that this maximum element will be one of the leaf nodes, and we have 512 leaf nodes, right? So we have to find the maximum from this, right? So let's assume you have just 5 elements, maybe A, B, C, D, and E. 5 elements. Let's assume you have 5 elements and you want to find out the maximum of these 5 elements. Then how many minimum comparisons are needed? Minimum comparisons are needed. So the idea is you assume that A is the maximum element. So you can directly assign the maximum element is equal to A. Okay. Then you compare maximum element with B. If B is greater than the maximum element, you will interchange the value. Then you will compare with C, then D, then E, right? So finally, you will have the maximum element here. So if you have 5 elements, you have to basically do only 4 comparisons, right? So that you can even recursively you can think about it. If you have only one element, then the maximum you can find it in 0 comparisons, because you have only one element, then that will be the maximum, right? If you have 2 elements, right, then you need to do only one comparison to find the maximum, right? So if you have 3 elements, then from 2 elements you can find the maximum in one comparison, and again from here you can find the maximum in 2 comparisons. So what I'm saying is, if you have 100 elements, then to find the maximum you have to do 99 comparisons. So here you have 512 elements. So to get the maximum you have to do 511 comparisons. Okay, so the answer should be 511.